Hey folks, Dr. G here. Today I'm really excited to do a video on Planck's solution to the ultraviolet catastrophe, which ultimately led to the discovery of quantum mechanics. So what do I mean by the ultraviolet catastrophe? Well, some physicists were doing experiments where they would heat things up to a really high temperature, and they would get so hot that they would begin to glow. And then they had devices where they could measure the different wavelengths of light that were coming off of the glowing hot objects. And if they plotted the intensity of the different wavelengths of light they were seeing as a function of the wavelength, they would get distributions like you see on the screen. So these objects that they were heating up are called blackbody objects. So why the name? Well, if you think of an object that appears black to you, it appears black because it's absorbing all wavelengths of visible light. So the idea of this is an object that not only the visible light, but any light you shine on it gets absorbed. Now, the goal with these experiments was to heat up objects that absorb all wavelengths of light, so that basically as they heat, the light you're measuring is only coming off of the object due to its temperature, because you've heated it up, right? If you heat up a piece of steel or something, it starts to glow red. So again, blackbody radiation refers to the electromagnetic radiation emitted by an idealized object that absorbs and emits all incident radiation perfectly, with its spectral distribution dependent only on temperature. At the molecular level, one way to visualize a blackbody object is to think of a whole bunch of harmonic oscillators. So what do I mean by harmonic oscillator? Well, think of a mass bouncing up and down on a spring, right? Something that jiggles, right? Matter all jiggles, and the hotter it gets, the more vigorously it jiggles. And if you think of these masses on the end of these springs having a charge on them, right? Well, if you have a charge oscillating back and forth, a charge moving back and forth, well, that's an electric field moving back and forth. And if you move an electric field back and forth, you also have a magnetic field moving back and forth perpendicular to that. And what is that? You've heard this before, maybe. If you have an E field oscillating one way and a B field oscillating the other way, it's light, right? That's light. So basically, if you think of these harmonic oscillators jiggling back and forth, that's going to produce light. And again, these blackbody objects, the only light coming off of them is due to these jiggling harmonic oscillators that make up the mass. Here's a cartoon I created showing roughly how you can think of a blackbody experiment being carried out. So you see the incident radiation source shining in there, and then once it's in there, it bounces around all over the place. So this is to kind of show that, okay, instant radiation gets absorbed and bounces around, right? Importantly, it's not getting reflected, right? It's bouncing around inside of it. So the blackbody here is hollow, so that's important too. So if you imagine incident radiation coming in there, heating that thing up, and it's all that energy is getting trapped in there, and basically the harmonic oscillators that make up that object start jiggling more and more vigorously, and it starts to glow, right? In the image here, it's glowing orange. And you see that light comes out, and then it hits a prism. What does a prism do? It splits the incident light into its spectrum. And if you look real carefully on that detector that I put in the image, there's some little dots in there, and those represent photodiodes, right? So these little circuits you can make that detect whether or not light is hitting, right? They can measure the intensity of the light. Well, if you've split the spectrum, then you can use the position of where it hits to know what frequency you're getting based on which sensor it hits. So this is something called a photodiode array. And of course, there's other ways to do this, but this is just one example that I think works really well in this sort of cartoon representation, so you can at least think about what's happening. So let's look more at these distributions here. Well, here we see another example of similar distribution. So the one that I started with is actually a type of blackbody radiation experiment that you can carry out pretty routinely in like maybe a college laboratory or maybe a high school. So let's return to these distributions that show which wavelengths of light are being detected for given temperatures and which are not. So here we show three different distributions for 3000, 4000, and 5000 Kelvin. And we see that it has this roughly kind of like a Boltzmann distribution, if you've seen one of those before. It has roughly that kind of shape. So the distributions are shown with the colors, but if we look at the black line, this was the theory that predated Planck's theory, right? So this was the best theory they had before Planck's came along. So this is the Rayleigh-Jeans law. If we look at the Rayleigh-Jeans law at really long wavelengths, it does an okay job at predicting the wavelengths you'll see for different temperatures. However, look what happens for shorter wavelengths, in particularly in the ultraviolet region. Notice anything wrong? Well, this law predicts energy going through the roof, right? It actually predicts energy going infinite for really short wavelengths. So obviously this can't be right, and I often like to check the Wikipedia post on all sorts of topics that I teach, and so the Wikipedia page for this topic says that this is clearly unphysical as the total radiated power of a cavity is not observed to be infinite, a point that was made independently by Einstein, Rayleigh, and Jeans in 1905. And, you know, you look at this and it's kind of like, no kidding, like, dude, I don't know. I find it surprising that 3 people had to confirm this, but I guess that's probably the paper that came out at that time. And they said, hey, I think we're doing a good job with long wavelengths, but yeah, we've got a problem here in the ultraviolet region. And then along came Max Planck to the rescue. So here we see Max Planck's expression, the Planck law, that shows the power density that we expect for a given temperature as a function of its wavelength. So again, looking at the image here, we can kind of think as temperature as more of a parameter, right? We plug that in once, and then we plot the different wavelengths that we see, right? The intensity goes up for some wavelengths and down for others if you don't see as much of it. And the particular quantity being measured here is power density as a function of wavelength. And later, we're going to get into exactly why this is the case. But let me ask you a question first. This is a question I love to ask my students. If we look at this equation, what are the units for the part of the equation in the blue box? Think about that for a second. What do you think about the units here? Is it energy per time or is it unitless? If you said unitless, you've got it, right? And I'm sure you knew it was unitless because all of the variables and parameters, whatever we have in that part of the box, is in an exponent, and exponents can't have units. You can't have a unit in the exponent. So if you don't know, now you know. Exponents can't have units. The simplest way to prove this to yourself is look up the Taylor series for an exponential function, and you'll see that if it had units, it would be equivalent to adding, let's pick length, right? Meters plus meters squared plus meters cubed. Right? So you can add a length to an area to a volume. No, that's crazy. You can't do that, right? So that's how we know that there's no units inside of that blue box there. So that means the rest of the equation must be supplying our units. Another question about the part in the blue box. Does this functional form look somewhat familiar? Well, Boltzmann tells us it better look somewhat familiar. If you've done a little statistical mechanics, it'll look familiar from there, that has a similar functional form to things you've seen before. But even if not, we have e to the constant over lambda times kT, Boltzmann's constant times temperature. So e to the something over kT. It looks a little bit like the Arrhenius equation, right? So here we have e to the minus energy over RT, and that's an activation energy in the case of the Arrhenius equation. So R, our gas constant, is a rate of exchange between energy and temperature, right? So it's like molar energy per temperature. So, you know, if you have, say, for example, kilocalories per mole is our energy, right? Or our energy per mole. So if you have kcal per mole divided by kelvins and you multiply that by kelvins, then you've got kcal per mole. And then if your activation energy is also measured in kcal per mole, then our units again cancel. So this is a functional form you're going to see all the time in physical chemistry, where we exponentiate in energy and then divide it by some rate of exchange between energy and temperature times temperature so that all of our units cancel. So if this is the Max Planck show, why am I talking about Boltzmann right now? Well, there's an interesting parallel that I'd like to draw between the two of them. You may or may not know this, but Boltzmann, people doubted his theories in his day because his theories were predicated on assuming that atoms are real. Right? This was still up for debate during Boltzmann's time. But Boltzmann made the jump to say that matter is discrete. For example, this glass of water here, right? If I take this glass of water, I dump half the water out. Then I dump half of that water out. I keep dumping half of the water out. Eventually, I could get down, in principle, eventually I could get down to, I only have 2 water molecules in the glass, and I dump one of the water molecules out, and I've got 1 molecule of water left. Can I still dump half of it out? No, of course not. If you divide a water molecule any more than what it is, it's no longer water. So basically matter is discretized. You could even say matter is quantized. At the macroscopic scale, this seems like a continuous thing to me, right? Like I can pour out as little as I want, but it turns out there's a small individual unit, one molecule of water, and if you go smaller than a molecule, it's no longer water. So Boltzmann discretized matter. He quantized matter. Planck quantized energy. So more specifically, Planck's derivation of this law assumed that the radiant object was made of oscillators that could only vibrate at discrete frequencies, i.e. vibrational energy is quantized. So the harmonic oscillators that make up this mass that's getting heated up, there's going to be certain frequencies that can vibrate, and that's it, right? So if you're at the lowest vibrational frequency it can do, and you want to go one up, and you go up to that one, there's nothing in between that. You can't get that to vibrate at a different frequency than the allowed frequencies. And there are macroscopic examples of this, right? Look at this guitar. If I play this open E string here, okay, that's an E right there. If I gently touch the string halfway up the string, that's an E an octave higher. But it's a different pitch, it's a different frequency. In fact, it's vibrating twice as fast. And notice, I don't have to hold anything down. It'll do this on its own, right? The string will play at this frequency, and it will play at this frequency, right? But if I wanted this sound right here, an F sharp, I have to shorten the string to do that. That's cheating here. I'm saying, what can this string do on its own that I can just hold the guitar out and it'll do it by itself? Here's another one. Right, so these are harmonics. It's kind of a similar thing. You can think about it. This is actually a closer thing to something else we're going to do involving a one-dimensional quantum particle in a box. But we'll get to that later. I'm actually going to do this lesson as a guided reading. So as I was looking around for materials, how I wanted to teach this, I kind of decided I wanted to do my own thing. So I just went ahead and wrote a document. It's about 10 pages long, and I have that available for download on my website. So I'll make sure I put a link in the description. So go look in the description to find a link to download the document. It's a PDF document that, I encourage you, maybe read it for yourself, maybe watch the video as you have it in front of you, whatever you like to do. So page 1 of the document has a lot of the background that I already talked about in the video, so I'm going to skip to page 2. Specifically, let's skip to the part where we talk about this notion that energy is quantized. So this was a leap that Planck had to take, similar to Boltzmann had to take that leap and say, I think atoms are real. I'm going to base my theory on that assumption. Planck did a similar thing. I'm not sure how he got that insight. Just to help you build some intuition for what I mean by this notion that energy can't be varied continuously, that it's discretized or it's quantized. Think about a knob that you can turn smoothly, like maybe on a radio in a car or something like that, a volume knob maybe. And at least as far as you can perceive, you can make the volume anything you want. It turns smoothly. And now compare that with this type of knob here. So when I was a little kid, there were TVs like this, that you would turn the knob and it would click into place. Right? And me just being how I am, I used to try and make it stop in between channels, but it doesn't want to do that, right? It clicks into place. So this is more how energy is, right? But sort of going between the two, now imagine that these clicks in place are so small that you can't perceive them. Well, that's kind of what's going on in daily life. When you say, well, things don't seem quantized to me. Like for example, if I lift up this glass of water and, if it's at this level versus this level, I feel like I can put it at any level that I want. And its energy, its potential energy due to gravitational potential energy is changing as I do that, right? It's not snapping into place at different levels. And that's because I'm at a massive scale compared to where quantum effects are super pronounced. So they never go away. They just average out to the point where they're imperceivable and things look classical. So remember, the world is quantum. It's just that these systems we typically think of as being, oh, that's a quantum system. Well, the quantum effects get most pronounced when distances are short, masses are small, temperatures are low, right? This is when the quantum effects tend to be most pronounced. Okay, so let's look at our very first equation here. E sub n equals nh nu. That thing that looks like a V is a Greek letter nu. That's Planck's constant times a frequency. And Planck's constant, that's our rate of exchange from energy to frequency, right? It's like energy per frequency. So oftentimes it's written in joules seconds, because joules times seconds is equivalent to joules per hertz, right? Because a hertz is a 1 over a second, right? It's an inverse second. So if we think of some system that has some characteristic frequency, right? Like think of the E string I played on the guitar earlier. If you think of that, that's our frequency nu. And Planck's constant converts that to energy because it's the rate of exchange for energy per frequency. So what's the n? It's our quantum number, and it can only occupy integer values, right? I can't set n to 0.75, right? It could be 1, 2, 3, 4, right? These are the allowed values for n, our quantum number. So if we have some system that has a characteristic frequency nu, Planck's constant never changes, it's a constant, then the energy levels it's allowed to occupy are going to be some multiple of that. So this is what we mean that the system's energy is quantized. And of course, if h nu is a really small number, these are going to be really tiny increases in energy that are maybe imperceivable at our size scale in our daily life, right? But things are quantized. Energy is quantized. So it's a simple equation, but I wanted to spend some time on it because this is the big assumption that Planck made that allowed him to derive his famous law. So now let's think about our black body radiation, right? You have this mass that you've heated up to some temperature and you want to know what's the total energy of that entire mass. Well, if by some tremendous stroke of luck you happen to know the quantum number of every single oscillator that makes up that mass that's so hot, then you can figure out the total energy this way, right? You can sum n h nu for each individual oscillator. Each individual oscillator follows that law, n times h nu. So if you know all the n's, if you know all the quantum states, you could just sum all these up and you have a total energy value. Now, if it seems unlikely you can actually know this about a system, good call. Yeah, this is impossible to do most of the time. But again, let's go back to Boltzmann. And the reason I want to go back to Boltzmann is because Boltzmann gave us an expression for observing a system at a particular energy value. So that's this equation here, the probability observing energy E. And yet again, we see this expression, right? We have E to the minus energy over KT, right? That's KBT, that's Boltzmann's constant. We don't always draw the B. So without that denominator there, we could say that the probability of E is proportional to E to the minus KT. Right? That basically the larger that number is, if you calculate that exponential for a given energy, that'll tell you relatively, right? It'll be proportional. So if you do it for two different energies, right? If one's bigger than the other, then that's the more probable one. So it's proportional to that. But if you want an actual probability, you need to divide by that denominator there, which is something we call the partition function. So for that, we have to sum over every possible energy. So we have to do that exponential function with every possible energy. And so that partition function is a normalizing constant. And it's normalizing because if I applied this equation to all the different possible energy values and I added all those probabilities together, I would get 1, probability 1. That's what it means to be normalized. But maybe that's a little abstract to think about these energies. So let's look at a much simpler example. Let's say we have a group of students. And in that group of students, I want to know what the average age is for those students. And we've got 3 students are 20 years old, 6 students are 21, and 1 student is 22 years old. So that's 10 students total. So if I divide the number of students that are each age by 10 in each case, so we have 3/10, 6/10, 1/10, and then I multiply that by their age, so 3 out of 10 students are 20, 6 out of 10 students are 21, etc. If you add that up, you get the mean. Now, the first way you probably learn to calculate means or averages would be to add the number you see the number of times, right? So you say, okay, I have 3 20-year-olds, 20 plus 20 plus 20 plus 21 plus 21 plus 21, etc. You can do it that way, but this is obviously much more efficient. And now let's say that I have a population of students as large as you want. A population as large as you want, but I happen to know that this is the fraction of each, right? 3 out of every 10 students is 20 years old, and I have 10,000 students. Well, I can calculate this the same way using these same ratios. Another way to think about this is in terms of probability. So if I have this group of 10 students in front of me and someone spins me around with my eyes closed and I point at one of them, right? The probability of me pointing at someone who is 21 years old is going to be 6 out of 10, right? It's 60% of the time I will point at a 21-year-old, right? That's sort of one way you can think about this. So then the expression below, I have the probability of observing a 20-year-old times the number 20, the probability of observing a 21-year-old times the number 21, right? So you have the age multiplied by the probability of measuring that age, of observing that age. And again, we get the same number here. So in this example, that thing we keep dividing by, our partition function, what's the partition function for the example with the students and the ages? It's 10, right? Because that first number, 3, 6, and 1, that's proportional to how often I'll see that age. But if I want it to be a probability, they have to be divided by 10. So that's basically functioning as a partition function here. So although the functional form for the probability using the Boltzmann distribution is perhaps a little trickier to look at, the principle is very similar. Okay, so building up from being able to calculate the mean value of a student's age in a group of students, let's look at calculating the mean value for energy. All right, because remember I said we have this mass, that we've heated up this mass that's composed of a bunch of harmonic oscillators, and if I knew all the quantum numbers, yeah, I could just add all that up. I'm not going to be able to get that, right? So what if I just knew the average energy? And then if I knew the average energy and I want to know how much energy I have, well, if I assume they're all at the average and I just multiply by the number of harmonic oscillators, I can get a total energy that way. So with that in mind, let's look at this expression for the average energy. So when you put something in brackets like that, right, the way that E is, that means average, or more precisely, it's often called the expectation value. So now looking at this expression for the average energy, it's very similar to the students and the ages. If you look inside of the sum, you have that energy value that you can measure multiplied by the probability of seeing that same energy value. So just like we have 3 out of 10 times 20, because 3 times out of 10 you'll observe a 20-year-old, similar thing here. You have e to the n times the exponent with e to the n, because it's the energy you're going to observe times the probability of observing it. And again, it's divided by the partition function so that each probability is normalized. You say, well, we have all these different values in the top and you only divide by it once. Well, the partition function is always the same. So if you look at those examples with the students, I could factor out the 10 and do 3 times 20 plus 6 times 21 plus 1 times 22, add all that up, and then divide that once by 10. You'll get the same answer. So that's a similar thing here, where basically that partition function is not changing. Therefore, we can divide by that just once in the denominator. So Boltzmann has given us an expression for the average energy of a harmonic oscillator in this big ball of harmonic oscillators that we're heating up and measuring the intensity of each wavelength coming off of that. Next, let's combine Planck's idea to have these quantized energies that are some integer n multiplied by h nu with Boltzmann's expression for the mean energy. Now, if we look at this expression, we say, great, we have an expression for the average energy. All I have to do is take these two infinite sums. Well, all right, good luck with an infinite sum, right? But if we look closely at these infinite sums, we recognize the geometric series. So as you've seen in your math classes, there are some infinite series that actually converge to a finite amount. So if we define x as e to the minus h nu over kt, then we can find a finite value for our infinite sum. And note the constraint for our geometric series here, that the absolute value of x is less than 1. So is this satisfied? Well, we have a negative exponent, and h is a constant that's non-negative. A frequency, negative frequencies aren't a thing, right? So frequency is positive. Boltzmann's constant is positive, and temperature is positive. Now, I know I have a video where I talk about negative absolute temperature, but it's an extremely rare case, right? So it's safe to say that absolute temperature, for our purposes here, you can't get negative Kelvin, right? That's a very specific thing that only applies to a couple very specific systems. So this expression, we're definitely going to assume that temperature also cannot be negative. So it turns out e to the minus anything here is going to be less than 1, so we're good to go. All right, so that takes care of the denominator. Now, if we look at the numerator and we think of this same definition of x and this same geometric series, how is that related to the numerator? Well, our sum now, instead of just being the sum over x to the n, now we also have h nu n times x to the n. So it's a little different, but h nu is a constant, so we can always factor that out of a sum. So that comes outside the sum. And now we've got n times x to the n. Well, if you think of that, you know, when you bring a numerator down and multiply by it, does that remind you of something? A derivative, right? So if we think of this original geometric series and its finite solution, if we just take the derivative of both sides with respect to x, and of course we're using the same definition of x as before, but we'll put that back in later. Well, that d dx operator can distribute through that entire sum, right? So then for each one, you're going to have n times x to the n minus 1. And then on the right side, you're going to have 1 over 1 minus x squared. So let's take this expression in terms of x and plug what we defined x as back in. So once we do that, we realize that if we multiply both sides by nh nu, it looks like the expression we were trying to get earlier. So now for the numerator as well, we have a finite value instead of an infinite sum. So we have a finite value for the numerator, a finite value for the denominator. Let's put them together. Then once we do that, we can simplify a little bit, and now we have an expression for the average energy. And again, this is the average energy for a single oscillator in this whole group of oscillators, right? Often we'll call that an ensemble, like a group of musicians is an ensemble. All these oscillators together in this mass. If you want to know the average energy of any of those oscillators, this is how you get it. Now remember, our goal here is to figure out the power density as a function of lambda, the wavelength, right? That's what we're after. But of course, power is energy per time. So if we can get energy density, that can help, right? So we have an expression for the energy of individual oscillators. In fact, we know the average energy for any one oscillator we pull out of our ensemble. And again, if I want to know what the energy of my mass is, right, that whole ensemble of oscillators, if I know how many oscillators are in there and I multiply that by the average energy of one oscillator, then I know the energy of the entire thing. And similarly, if I know how many oscillators I have per unit volume and multiply that by that average energy, then I have an energy density. And that density of oscillators per unit volume, we call that a density of states. Because as we know, matter is made up of atoms. Therefore, if you look at all the different modes that they can vibrate at, there's a finite number of them, because you can't keep zooming in. Eventually, you know, you're going to get to a subatomic scale, and then you can't get individual oscillators anymore. So there's always going to be some density of states. Now, full derivation of this density of states expression requires us to get into some solid state physics that I don't think really fit in this lecture, but we'll do another one later to cover that. So for now, just know that our expression for the density of states is 8 pi nu squared over the speed of light cubed. Thus, our energy density, U of nu in T, we can get by multiplying density of states by the average energy of one harmonic oscillator. And notice with the units, multiplying the density of states by energy gives us the units of energy per volume per unit frequency. So we now have an expression for U, the energy density as a function of the frequency and temperature. So an energy density, it's not a power density, but we're getting closer. So now we have to switch up our thinking a little bit, and instead of thinking of the black body emitting radiation, let's think about detecting it. So at the detector, thinking of that image I showed you where we have the light going through a prism and then hitting photodiodes to see what intensity of light we're getting at different wavelengths. So now we have to introduce a new type of quantity called spectral energy flux. Well, flux means flow, and spectral having to do with the spectrum, or a set of wavelengths. So for a given wavelength, what's the flow of energy through some surface? So think of that sensor surface, the energy flowing through that. That's what we're after with spectral energy flux. Well, flux is a flow. So if something's passing through something, obviously if it's going through faster, that's going to be a higher flux. So now we have to concern ourselves with the speed at which it's flowing through. So here we define energy flux as energy density times the speed, right? How dense is it? How much is flowing through that at a given moment? And how fast is that density flowing through? They both have to factor into this. So it's energy density times the speed. And what speed do you think the light's going? The speed of light, right? So you have to multiply by c. So we have an expression for energy density. You multiply by c. You might think, okay, done. Well, not really, right? That's not quite it. If the radiation was going all the same direction, we could do it this way. But remember, we have this sort of this hollow sphere that we're heating up. And, the radiation can go all sorts of different directions. In fact, it can radiate inward inside of the sphere, right? If you have a particular oscillator that's about to emit its energy, right? It could go outwards, it could go inwards. So take a look at this image on the screen. I spent a bit of time on this thing. I actually really like this image. What this is intended to show you is that light leaving the different surfaces of this object, only a quarter of it actually has any chance of going towards the detector. So first let's consider the fact that if one of these oscillators is about to emit its light, it could emit its light outward or inward. So note that we have two sets of arrows here, right? We have some arrows pointing into the sphere and some arrows pointing out of the sphere. Well, regardless of what direction the arrows are going, that all contributes to the energy density of that object. But the ones going inwards are never going to be detected by the detector, right? Because they're just going to keep bouncing around inside, but that's still radiated energy. So what we have to do is we have to say, okay, half of our light's going to stay inside, right? Half of our emitted, our blackbody radiation is just going to radiate inward. So right there, one half gone. And then we look at the half that's pointing outward. So the half pointing outward, well, the ones on the right side of the sphere, they're going to go the wrong way, right? So things go in that direction, they're going to go the wrong way. So basically, then half of the outer one. So you have half times half is a quarter. So really the expression is C over 4 times the energy density. And note, although I drew all the arrows pointing, straight off the surface, right, normal to the surface, they don't necessarily have to go that direction. But if it's on the wrong side, no matter what angle you go, right, you're not going to find the detector. So bear in mind, this is only showing like what parts of the surface are actually viable for potentially producing a photon that reaches the detector. Also notice I drew that one long, thick orange arrow to just kind of single one in particular out, and we see that the flux you would measure from that particular emission is only going to be the component along that x direction, which of course we get using the cosine of the angle. So that's one expression for spectral energy flux. Next, we're going to find another expression for spectral energy flux, and we'll set them equal to each other. All right, so the second expression for spectral energy flux, notice we've got that B of nu. Well, that's the thing we're after. That's the thing we're trying to get, this power density, also known as spectral radiance. So in that image, I showed you all those different vectors normal to the surface of the sphere pointing outwards. And I singled that one out and said, okay, here's this one arrow here and its x component's going to hit the detector. Well, that's just one particular angle. We need to now integrate over all the possible angles. And there's a specific way we need to treat this. So we're taking this integral using an integration element you may or may not have seen before, called the solid angle element. So thinking of a standard integral where your integration element is like dx. Well, that's sort of a width. That's a width in that one dimension because it's just a one-dimensional thing that you're doing, that you're integrating over. You're basically calculating a whole bunch of areas, right, where you have a little dx, and then you get the height from the function. Right, so you have a bunch of little rectangles is one way you can kind of think of it. You're getting the area under the curve. Well, this is volume. All right, we're in a three-dimensional space here. And in this particular case, we're in spherical coordinates. So for us, this tiny change, right, you can't just have that be in one dimension. That won't be helpful to us. And so that's why I've included this graphical representation of the solid angle element. So just like you think of dx as like the smallest change you can make in that one dimension, think of this as like the smallest change you can make for this like wedge-shaped thing. So if we substitute in our solid angle element, we get this integral here, where first we're integrating over theta from 0 to pi over 2, and then from 0 to 2 pi for phi. So in our expression here, we substituted in our solid angle element, and we're integrating over theta and phi. And of course, our b of nu as a function of t, that comes outside, right? Because that function is not a function of theta or phi. So now these limits of integration, why am I integrating theta from 0 to pi over 2, and I'm integrating phi from 0 to 2 pi? Why is that? Well, I created this little visual representation here to show you. So think about that yellow surface as a little chunk of the surface of our blackbody radiating object. And so z, that arrow z, that's basically like if we're coming straight off, right? Normal to that surface. Well, normal to that surface, that is angle theta of 0. So you think, okay, well, how far down can I go? Well, pi over 2. right? If I went all the way down to pi, I'd be pointing into the interior of the object, and that's we can't, right? It's not, we can't pick that up with the detector. So basically, as soon as you get down to the surface, you're going in directions that can't be detected. So that's why it goes from 0 to pi over 2. Now in the phi direction, if you imagine rotating that around, any of those directions will work just fine. So that's why we integrate phi over the entire range from 0 to 2 pi. So after we take that integral, it integrates to the constant pi. So we have I sub nu equals pi times b sub nu as a function of t. So we have two expressions for the energy flux per frequency, right? So let's set them equal to each other. Now, if we simplify, we have c over 4 pi times u of nu and t. But of course, that's our energy density function. So we could just replace that with the value that we figured out earlier. And now finally, we have an expression. This is a perfectly fine way to describe the power density, but it's in the frequency domain, right? So that plot that we showed earlier was in the wavelength domain, right? So it's in terms of wavelength. We want to see the power density in terms of wavelength, not frequency. Right now we have power density in terms of frequency. So let's convert that to wavelength. Well, let's use this well-known relationship, often called the de Broglie relationship, of nu equals c over lambda. So nu, the frequency, equals the speed of light over the wavelength. So if you were thinking we could just kind of plug this relationship in, not quite. It's a little more complicated than that. Specifically, if we think about it, there's only so much power density there. So whether you integrate it over all of the possible frequencies or all of the possible wavelengths, well, these are just different viewpoints of looking at certain regions of the power density. But the total power density has to be the same if you integrate over all frequencies or all wavelengths respectively. So in going from one representation to the other, they're actually related by the way they would be integrated. So in order to do this, we have to figure out that small change, right? d nu versus d lambda. We have to figure out how those two are related to each other. So if we start with the de Broglie relationship and you differentiate both sides, we get this expression. And then we're going to do something kind of unconventional now. We're actually just going to ignore a negative sign. You say, well, how are you getting away with that? Well, frequency. Can you have a negative frequency? Is that really a thing? Negative frequency? If I play the note minus 440 hertz, right? 440 hertz, that's an A, right? The note A. Play minus 4, that doesn't have meaning, right? So you don't have negative frequencies. Also, lengths, the wavelength, a distance is, you can't have a negative distance either, right? If you say, oh, what town is negative 50 miles from here? What does that mean, right? So these things can't be negative anyway. So we're actually going to just drop that negative sign on purpose because it's not physically relevant. So this is the sort of thing that would probably really bother a mathematician here. But in terms of physics, you know, it's mathematics constrained by physical realities here. So we can actually ignore that negative sign. So now we have a differential for nu and for lambda. So if you want to integrate something in terms of lambda instead of in terms of nu, you can't just have the d lambda. You have to have c over lambda squared times d lambda. So looking at this expression, d nu equals c over lambda squared d lambda. So now we have an expression with d nu and d lambda in it. So now we can use that to connect two expressions for spectral radiance with respect to lambda or respect to nu. So we take advantage of this relationship that if you were to integrate over all the spectral radiance, if you have all of it, whether you're in the frequency domain or the wavelength domain, it shouldn't matter, right? You should get that same quantity. So in the expression, we don't actually take the integral, but we've kind of set it up. We could integrate both sides if we wanted to, but we don't. Instead, we rearrange it because we have a relationship for d nu, d lambda. And then instead, we can swap that in. So now we've finally figured out that if we want our spectral density or our power density in the wavelength regime, lambda, we have to multiply the frequency one by c over lambda squared. So now let's get our expression for power density in the frequency domain and multiply it by that and simplify. So finally, at long last, we have Planck's law in wavelength form. And so Max Planck solved the ultraviolet catastrophe and gave us this expression. And out of that came the invention of this idea that energy is quantized, right? So this was the quantum revolution got started with this. Energy is quantized. That's one of the important things way back in the beginning of that derivation, right? This expression came out of that assumption that we could sum over these quantized energies. Also, Planck's constant that's in here, right? That established this rate of exchange. Like, how do we go between energies and frequencies? Planck's constant. It's in units of energy per frequency. And so we see this, for example, in what we call the Bohr frequency relation, right? Where we want to say, okay, there's some delta E, some change in energy. Well, we know that difference in energy is directly proportional to the frequency. So this Bohr frequency relation that features Planck's constant tells us that energy and frequency are proportional, where our constant of proportionality is Planck's constant. Again, it's like a rate of exchange. Cool example of this, fireworks, right? When the explosion goes off, they put metals into fireworks, and those metal atoms get excited to a higher energy state, and then they relax back down. And when they relax back down, they give that energy back off. We see that as light. And these different energy levels that you see depending on the metal, that's what affects the frequency that we see, the wavelength of light that we see. Another famous equation featuring Planck's constant, the de Broglie relation. So this shows that wavelength and momentum are inversely related. So if you have a lot of momentum, you've got a very short wavelength. And again, the whole world is quantum. So if you go for a run, do you have a wavelength? Yeah, but it's so small, it's like, who cares, right? Because if you look at this relationship, it's going to be very small. So you should calculate your wavelength sometime. And you'll see why we would just approximate a person running as a classical object. We don't need to involve quantum mechanics to calculate the momentum of a person going for a run. All right, folks, I hope you enjoyed learning about Planck's law and his solution to the ultraviolet catastrophe. It not only solved one of the biggest mysteries of his era, but it launched the quantum revolution. And quantum mechanics is a massive, thriving field today, where not only in science, but even in engineering, people are applying quantum effects in some products. For example, quantum dot OLED televisions, the organic LED with the quantum dot technology, there's a quantum effect there. Additionally, you may have heard of quantum computing, which is a growing field as the hardware starts to become more and more feasible. They're very difficult to build, but a few different groups are making some serious progress on that. All right, folks, thanks for watching. I'm Dr. G, and I'll see you in the next one.